In this section, I'd like to talk about Turing machines. Turing machines are simple, but powerful. They are as powerful as your computers. But for complex tasks as your computers can do, it takes a lot of details to describe the Turing machine that can accomplish the same task. So usually, Turing machines are described in a high level with English. But just to show you that those high-level descriptions have a low-level state diagram for them, I'm going to talk about the details and formal definition of Turing machines with examples. Hopefully, after this section, you have a good understanding of Turing machines and their working mechanisms. We will cover 5 parts today. We talk about the language hierarchy first, then move to the formal definition of Turing machines. With the definition, we then talk about how the machine runs on input strings and the languages defined by Turing machines. Finally, we use 2 examples to show how we construct a Turing machine to recognize a given language, both in high-level description and in low-level state diagram. Up to now, we have covered regular languages defined by DFAs or NFAs or regular expressions. The limit of DFAs is that they have limited memory. They can only use a finite number of states to store information. A sample regular language is the set of strings a to the n, where n is a natural number. After that, we talked about context-free languages, which can be generated by context-free grammars or recognized by push-down automata. A push-down automaton has unlimited memory, but information is stored in a restricted way. It is either stored using the finite set of states or the unlimited stack, but it only has access to the top symbol of the stack. A sample context-free language is the set of strings a to the n, b to the n, where n is a natural number. While DFAs cannot store arbitrarily large number of a's, a push-down automaton can use the stack to store them and match remaining b's one by one. Today we talk about a more powerful machine, Turing machines. It has unlimited memory and is more flexible dealing with stored information. Languages defined by Turing machines are called Turing-recognizable languages or recursively enumerable languages. But Turing machines are not omnipotent. There are languages that cannot be recognized by Turing machines. These languages are beyond the theoretical limits of computation. This is a topic in later sections. Now let's see how a Turing machine looks like. Visually, a Turing machine has an infinite tape as its unlimited memory. The tape is left-bounded. Each tape cell stores exactly one symbol. It has a tape head that can read and write symbols and move left and right on the tape. And it has a finite set of states, just as DFAs and PDAs. This is just the picturization of Turing machines. Next is the formal definition, just as we formally define DFAs and PDAs. A Turing machine is a 7-tuple, a set of states Q, a set of input symbols sigma, a set of tape symbols lambda, a transition function delta, a single start state Q0, a single accept state QA, and a single reject state QR. Note that Q, sigma, and lambda are finite sets. The special symbol, blank symbol, is in the tape alphabet, but not in the input alphabet. The input alphabet sigma is a subset of the tape alphabet lambda. And the accept state QA is different from the reject state QR. It is possible that the start state Q0 is an accept state or a reject state. Now let's take a closer look at the transition function. The transition function is deterministic, just like DFAs. If the transition function maps a tuple QA to a tuple RBL, the meaning of that is the machine is currently at state Q, the tape head is over a cell containing symbol A. According to the mapping, the machine writes symbol B replacing A on the tape, and it goes to state R. After writing, the head moves to the left. In this transition, if A equals B, then the tape head just reads a symbol without changing it. If Q equals R, then the machine does not change states. Let's see an example. Let's say the machine currently looks like the one on the left. If the transition function have delta Q1 0 equals Q2 1 R, then the machine will write 1 replacing 0 on the tape and goes to state Q2. After that, the head moves to the right. Now the machine looks like the one on the right. Now that we know how the machine transfers according to the transition function, we can talk about the computation of the machine on an input string W. Assume W contains n symbols, W1, W2, all the way to Wn. Initially, M receives its input W on the leftmost n cells of the tape, and the rest of the tape is blank symbols. The tape head points to the leftmost cell, and the machine starts at Q0. Once M has started, the computation proceeds according to the rules described by the transition function. A special case here is that when the head is at the leftmost cell, but the transition function says to go left. In this situation, the head stays in the same place for that move, even though the transition function indicates left, because there's no way to move left. When the machine starts on an input string, 3 outcomes are possible. The machine accepts the string by entering QA and halts, or rejects the string by entering QR and halts, or the machine loops. By looping, we mean the machine does not halt. Once the machine enters QA or QR, the computation is done. If the machine loops, then the computation is never done. The problem is, when the machine loops, we don't know it's looping. We cannot distinguish a machine that is looping from one that is merely taking a long time to finish. This is called the halting problem. This is a topic in later sections. To draw the tape, the head, and the state is cumbersome. For convenience, we use configurations. A configuration specifies the tape content, the tape head position, and the current state in one string. A configuration C equals UQV means the tape content is UV on the leftmost cells, followed by blank symbols everywhere else. The tape head is on the first symbol of V, and the machine is on state Q. We say a configuration C1 yields C2 if the machine can go from C1 to C2 in a single step, according to the transition function. For example, if the current configuration C1 is UAQIBV, and the transition function says delta QIA equals QJCL, then configuration C2 UQJACV is yielded. because the machine is at Qi and tape head points to A in C1. According to the transition function, it moves to state Qj, tape head replaces B with C, and moves to the left. Alright, now that we know the working mechanism, we can talk about the languages defined by Turing machines. A Turing machine M accepts input W if a sequence of configurations C1, C2 through CK exists, where C1 is the start configuration of M on W, each Ci yields Ci plus 1, and CK is an accepting configuration. That means QA is in CK. In general, if there is no requirement on the content of the tape when the machine stops, then the machine accepts a string so long as it enters QA at some time. The machine doesn't even need to read the whole input in some cases. The set of strings that M accepts is the language recognized by M. If a language L can be recognized by some Turing machine, then we call L is Turing recognizable. Okay, with all the definitions we have, let's use them. Given the language L, we construct a Turing machine that recognizes it. Say, L equals the set of strings with a chunk of ones followed by a chunk of zeros, and the number of ones is greater than the number of zeros. To recognize this language, the basic idea is, on an input string W, match a 1 and a 0 pair by pair from the two ends to the center. After all the zeros on the right are matched, if there are any ones left, then accept. We now describe this idea more formally and in more detail, but still in English. This is called a high-level description of a Turing machine. So, M equals, on input W, first, sweep left to right across the tape. Replace the leftmost one of the remaining input with the blank symbol. If no one is encountered, reject. Second, keep moving to the right, pass all the ones. If a blank symbol is encountered, accept. Otherwise, go to step 3. In step 3, keep moving to the right. Pass all the zeros until a blank symbol is encountered. If a 1 is encountered along the way, reject. Now that we have encountered a blank symbol, we have reached the right end of the remaining input. So, in step 4, we move to the left and cross the 0 left to the blank symbol. After that, move to the left. Pass all the 1s and 0s. If a blank symbol is encountered, that means we have reached the left end of the remaining input. So we go to step 1 for the next round of matching. Now we show the detailed state diagram of this machine. This machine has 7 states. The input alphabet is 0 and 1. The tape alphabet is 0, 1, and a blank symbol. Out of each state, we define a transition for each tape symbol. Alright, let's dive into the machine. State Q0 means equal number of zeros and ones are matched. If the head is now on a 0 or blank symbol, then it means the input string has equal number of zeros and ones, or more zeros than ones. In this case, the machine goes to state QR without changing the tape input. And it doesn't matter which direction the head moves. What it matters is the machine goes to state QR to reject the string. If the head is now on a 1, then it moves to state Q2 and replace the 1 with a blank symbol. After that, the head moves to the right, trying to match a 0 at the right end. State Q2 means there are at least one more ones than zeros. It keeps moving to the right while reading ones on the tape, but stays at Q2. If the head reaches a blank, that means there is no more zeros to match. The input string has more ones than zeros, and the machine goes to QA to accept the string. If the head is on a 0, the machine goes to state Q3 and passes all zeros encountered because the goal is to reach the rightmost 0. State Q3 means there is at least one 0 to match the one crossed in the left. From state Q3, if the head reaches some symbol 1, that means the input string is misformatted, so it goes to QR to reject the string. On the other hand, if the head reaches a blank symbol, that means the right end of the remaining input is reached. The machine goes to state Q4 and moves its head left, about to cross the rightmost 0. Transition from Q4 to Q5 replaces the rightmost 0 and moves the head left. On state Q4, transitions for one and blank symbol are omitted because the machine has passed at least one 0 to reach Q3 and a single blank symbol to reach Q4. So it is not possible to see a 1 or blank symbol from Q4. But to keep the integrity of the machine, we can add those transitions to QR. In Q5, the machine has matched a pair of 1 and 0. Now the job is to go to the left end of the remaining input for the next round of matching. So on state Q5, the machine keeps passing zeros and ones until the head reaches a blank symbol. In that case, the machine goes to Q0. Now it is ready for the next round. That's all for the state diagram. It looks like a push-down automaton. The only difference is instead of making changes to the stack in a PDA, it makes changes to the tape cells. Now let's test some sample strings. We will run the machine on some strings and compute each configuration encountered. There are 5 kinds of strings we want to test. The first 2 categories have misformatted strings. The next 2 categories have the correct format but violate the requirement for more ones than zeros. All these 4 categories of strings should be rejected. The last category of strings should be accepted. I'll use string 01 as an example. The start configuration is Q010. Now the head is on a 1. So following the transition from Q0 to Q2, the machine crosses the 1 with a blank symbol and moves head to the right. So now the configuration is blank Q2 0. Now the head is on a 0. Following the transition from Q2 to Q3, the machine passes the 0 and moves head to the right. So the configuration is blank 0 Q3. The tape content right to the 0 is blank symbol everywhere. So now the head is on a blank symbol. Following the transition from Q3 to Q4, the machine reads the first blank symbol and moves head to the left. Now the head goes back to the 0, and the state is Q4. So the configuration is blank Q4 0. Following the transition from Q4 to Q5, the machine crosses the 0 with a blank symbol and moves head to the left. Now it has matched a pair of 1 and 0. The configuration is Q5 blank blank. When the part right to the state in the configuration is blank symbols only, we can omit the blank symbols in the configuration. So we can just write Q5 in place of Q5 blank blank. Since the head is now on a blank symbol, the machine transfers to Q0 and moves head to the right, resulting in the configuration blank Q0. From here, the machine goes to QR because the head points to a blank symbol. Now the machine halts because it has entered a halting state, QR. Since this halting state is QR, the machine rejects the string 10. I will leave all the other sample strings as a practice for you. Now let's see another example. We want to construct a Turing machine to recognize the language of even-length palindromes. The basic idea is still to match symbols from the two ends toward the center. In the high-level description, on input string W, the machine zigzag across the tape to the two ends of the remaining input string to check whether these two positions have the same symbol. If they do, cross them, otherwise reject. If all symbols are matched, accept. If there is any mismatch, reject right away. Now let's realize this idea with the low-level state diagram. This machine has 8 states. State Q0 means some pairs of zeros or some pairs of ones are matched in the correct positions. Now the machine crosses a 0 with X and moves to the right. Then it keeps moving to the right, passing all zeros and ones until a blank symbol or an X is encountered. Since we cross symbols with X, now an X on the right also means the right end of the remaining input string is reached. So state Q2 means the right end has reached and the machine is about to cross the rightmost symbol if it is a 0. If it is a 1 or an X, a mismatch is found. The machine goes to QR to reject the string. If you decide to go to QR or QA, it doesn't matter what you do with the tape cell or which direction you move the head. The key is you are going to halt the machine with a decision by entering QA or QR. Once the machine reaches Q5, it has matched a pair of zeros from the top path. Similarly, if the left symbol read at Q0 is a 1, then following the bottom path, the machine matches a pair of 1s when reaching Q5. After that, the head should move to the left end for the next round. So it passes all the 1s and zeros until an X is reached in the left end. In that case, it transfers to Q0 and is ready for the next round. At Q0, if the head reads an X or a blank symbol, that means there is no symbols to match. So it goes to QA to accept the string. Now it's time to test some sample strings. I gave the computation paths of 3 strings for you to verify. That's all for today. Leave a comment if you have any questions.